So there were apparently lots of graduate students who haven't seen any other students for 3 years because of pandemic. So if this is like a Discord channel where you can talk to each other and go have beer, I was told, I don't know, like, so please join this Discord channel if you're a graduate student here from anywhere. Okay, so we are delighted to have Joel Kamnitzer, who will talk about basis in representation theory and cluster algebras. And if you have questions during the talk, I think, or after, I will come to you, you tell it to me, and I will speak it in microphone. I guess that's the easiest way to do it. Okay, so please, Joel.
Thank you. Thank you for the invitation. Sorry I'm not there in person. Here I had my oldest daughter make a drawing of what it would look like if I was there giving this talk. Maybe it's some kind of generic math that the guy's talking about, not bases in representation theory. But so yeah, again, thanks for the invitation. It's actually the first time I've spoken at a Algebraic Combinatorics conference in a long time. But maybe the origin of this talk, let me say, is that about 6 years ago, I was in Toronto in a park with David Spire. And David asked me, so are representations theorists very excited about the new work of Gross, Hacking, Kiel, and Kinsevich about bases for cluster algebras? And of course, I said to him, oh, what new work of Gross, Hacking, Kiel, and Kinsevich? Because I hadn't read the paper or been aware of it at that point. So anyway, gradually I became aware of their work and I tried to understand how it was related to stuff that I knew about. And maybe this talk is a kind of partial progress report, although as you'll see, there'll be a lot of open problems. Okay, so feel free to interrupt at any time with questions, either online people or in-person people. I guess we'll have a way of asking the questions. Okay, so let me begin. Well, I'm going to begin. So I'm working in representation theory, not in cluster algebras, really. So I'm going to begin in representation theory. Please let me know if you can't hear me or see the slides properly or something. But hopefully the technology works well. Okay, so let's begin. We'll start with a semi-simple group over the complex numbers. So our main example of such a group is the group of n by n invertible matrices, SLN. These groups have very well understood representation theory. So in a nutshell, the way it works is like this. There's a set called the set of dominant weights. And for each dominant weight, there's a irreducible representation. What do the sets look like? It looks like the set of dominant weights is an integer points in a cone. For example, when G is SLN, then we have the space of n integers, which are weakly decreasing. Given a representation, there's like two sort of combinatorial things that we're going to do. The first combinatorial thing is we're going to decompose it under the action of the maximal torus. So we have a maximal torus in G. When G is SLN, this torus is simply the diagonal matrices. And this decomposes into some subspaces that are consisting of eigenvectors for this maximal torus. Another thing we're going to do is, given two such irreducible representations, we can form their tensor product and decompose that into irreducible representations. And there's some multiplicities that'll be here called tensor product multiplicities. So the first problem, famous problem, is determine combinatorial formulas for weight and tensor product multiplicities. So weight multiplicities means the dimension of these spaces, weight spaces. Tensor product multiplicities means these numbers appearing here. So this problem is not open. I'll have some not open problems in my talk too. This one's not open. But it's not, wasn't solved, even though this basic framework of the representation theory of semi-simple groups goes back, I don't know, probably like 100 years to work of Hermann Weyl and others. This problem was only really solved in the 90s, I would say. Well, first, it was solved earlier for SLN. So in the case of SLN, you can find these weight and tensor product multiplicities by counting certain Young tableaux. So in particular for tensor product multiplicities, this takes the form of the famous Littlewood-Richardson rule. You count these Littlewood-Richardson Young tableau. In general, for arbitrary semi-simple algebras or groups, it was solved by kind of independently, I would say, by Berenstein and Zelevinsky and also Littleman in the 90s. So not super recently, but not super long ago either. So the idea of their approach, maybe especially the idea in Berenstein and Zelevinsky, but implicitly in Littleman as well, is if we want to find the dimension of these, let me just scroll up 1 second. If you want to find the dimension of these weight multiplicity spaces, then you can try to find a basis for your representation, which is adapted to this decomposition, and then just count how many basis vectors are in each weight space. These spaces here are called weight spaces. And you can use that same idea for tensor product multiplicity spaces because of the following trick. So here's the trick. There's a way of embedding this tensor product multiplicity space. So first of all, this number, tensor product multiplicity number I mentioned before, this C lambda mu, this is actually the dimension of this space over there, okay? Maybe it's a little strange to write this. Okay, C lambda mu is a dimension of this tensor product multiplicity space. And this tensor product multiplicity space can be embedded back in one of the representations that you're taking the tensor product of. And how does it work? Well, intuitively, these HOMs are given by what's called highest weight vectors. So every such representation V lambda or V mu has a highest weight vector. And so there'll be some highest vector of highest weight vector of weight nu sitting in here. And you expand it as V tensor V mu. And then you just remember the V part. Or in terms of a formula, it's given over here. Anyway, the detail is not super important, but what's important is to see that there's a way of embedding this inside of the given representation, and not just in some arbitrary way, but you can even describe its image. So the image is vectors satisfying a certain condition. The condition is that they're annihilated by powers of these elements EI. So EIs are Chevalier generators of the Lie algebra. In the case of SLN, these EIs are just the matrix where you just have an elementary matrix where you just have one just above the diagonals. So our goal then is to find bases which are weight bases, so they sit in these weight spaces and are adapted to these conditions. So that led to the definition. This definition is due to, I believe, to Galfand and Zelevinsky from the 80s. So a basis of a representation is called good if it's a weight basis and if it's compatible with all these subspaces. So for any EI and any K, there's they give you this filtration, and you want your basis to be compatible with that filtration. So it intersects to a basis of each one of those subspaces. And if you have such a good basis, then you can use it to solve this tensor product multiplicity problem because of the following, well, from this lemma, then it leads to the following statement: a good basis for V lambda restricts to a basis for each of these tensor product multiplicity spaces. So each of these HOM spaces is embedded in the representation. Then we have a basis of the representation, and it's compatible with those embeddings. So it gives you a basis just by restriction. Okay. So we're going to need a slight refinement of the notion of good basis, which is called perfect basis. So to define perfect basis, I begin with the following definition, which is given a vector, we're going to take its nilpotence orbit with respect to EI. So the largest number so that EIK of V is not zero. So this epsilon I of V, it could be zero, it could be some positive integer. So here you have some vector V, you apply EI, you apply EI again, oops, then you get to zero. So this guy would have epsilon I equal to zero. So now this new definition of perfect basis, I believe is due to Berenstein and Kazhdan. So a good basis is called perfect. If whenever we have a vector in the basis and one of these are the vertices of the Dinkin diagram, this capital I, they index these Chevalier generators. If whenever we have a vector in the basis, then either EI of B is 0. So either we're actually at the end of this, like applying these EIs, or it's not 0, in which case there's some other basis vector. And the simplest thing I could say would be that EI of B equals that other basis vector, but it's not true for two reasons. One, a not very important reason, that there's a scalar. But secondly, more importantly, there's a lower order term, which comes out. And what makes this term lower order is just that its epsilon I is smaller than it could be, than it should be. Like it's less than epsilon I of B minus 1. So why is this perfect basis good? Well, basically the reason why they're good for the purpose of this talk, or in general, is because they lead to combinatorics. So where's the combinatorics? So given a perfect basis, so it's a basis of a representation with this property that it's almost preserved by the actions of these EIs, we get a combinatorial structure. So we remember the finite set, we remember the weight of each basis element, and we remember the data of these EI tildes. So this is like the leading order behavior of the Chevalier generators on the basis. So here's an example. And usually you depict this data as a graph. So sometimes this data, I never wrote this down, but this data is called a crystal. This combinatorial structure is a crystal. And sometimes called crystal graph. So here's an example. Take SL3 with the adjoint representation. So SL3 acting on its Lie algebra. That's the Lie algebra is just 3 by 3 trace 0 matrices. And there's 8 basis vectors, as you might expect. So you might have seen a picture of this weight diagram. Sometimes people draw a picture like so of the weight diagram of the representation or something. I don't know. Anyway, so so basically what I'm doing is I'm taking this weight diagram. Maybe I'll put numbers. Maybe that makes more sense. So this weight diagram, and I'm enhancing it to a set along with these arrows which connect you between different these weight spaces. So for example, this 2 in the middle and those 2 dots in the middle, this is related to the diagonal matrices inside of this SL3. So this is 3 by 3 trace 0 diagonal matrices, so it's only 2-dimensional. Okay, so so every time you have a perfect basis for a representation, you can extract this combinatorial structure. And what makes this attractive is that this combinatorial structure is something you can study independently of the representation. And in fact, what's maybe is not hard to prove, but a nice fact, and I should have attributed this again to Berenstein, Kajdan, that if we have 2 perfect bases for a given representation, they might be different as bases. They might actually be different vectors, but they give you the same combinatorial structure in the end. So no matter how I would pick the bases of this representation, I would still get the exact same graph afterwards. The truth is, for this representation, there is only one perfect basis. So it's not, but in other cases there are. Okay. So this leads to a new problem, which is going to be, in some sense, a reformulation of our previous problem about tensor product multiplicities, which is, well, also not quite open, but we're getting towards open problems soon. So the first problem is to find perfect bases for each representation. And the second problem is to understand the combinatorics of the resulting crystals. So how can you describe these kind of graphs which come out, and how can you find these basis vectors in these weight spaces? Of course, in this example here, it's obvious how to find the basis vectors here and here because they're only one-dimensional vector spaces. I mean, usually things don't matter much up the scalar. And in the middle here, well, it's not so obvious because it's a two-dimensional vector space. So you have to find a basis. So how can you find perfect bases? Even how can you show that perfect bases exist? And how can you give combinatorial descriptions of the resulting crystal graph? So one, sounds like it might be easy. I just want a basis. I don't know, I just pick some. But actually it's hard to find these bases, even hard to even prove sort of abstractly that the bases exist. So for a good basis, then maybe it's, well, at least for SLN, there was an old work of Mathieu about proving the existence of good bases, but in general, it's not so easy for perfect bases to prove their existence and to construct them. So in particular, there's like no really elementary way of constructing them. So all the constructions involve some kind of maybe complicated geometry, algebraic geometry. So there's three maybe known constructions, at least that I know about. Two of them are due to Lustig. They're the dual canonical basis and dual semicanonical basis. You could say the dual semicanonical basis involves the geometry of quiver varieties. The dual canonical basis, you could say also is at least one definition involves the geometry of quiver varieties, or you could say it involves the theory of quantum groups, or you could say it involves something called categorification. So there's somehow the dual canonical basis is a bit canonical and that has multiple ways of constructing it. Whereas this dual semicanonical and the MV basis, Mirkovic-Vilonen basis, they come from a specific geometry. So again, this dual semicanonical basis, this comes from quiver varieties. And this MV basis, this comes from affine Grassmannians. Okay, so that was the first question, finding the perfect bases. The second question is how to make combinatorial models for the crystal. So that there's many combinatorial models. For example, in type A, you can use semi-standard Young tableau, and in other types too. Sometimes there's models involving semi-standard Young tableau. There's many other ones. Two ones which I'll maybe mention as the most famous one is one, the theory of Littleman-Paz. So that was used by Littleman in his work and subsequently. And the second is the theory of Mirkovic-Vilonen polytopes, first introduced by Jared Anderson. Here's a little picture of a model for this crystal that we mentioned above, the joint representation of SL3 using Mirkovic-Vilonen polytope. So each one of these dots above, scroll up, those dots, those black dots, each of them has been replaced by a single polytope. Here we have, some of the polytopes are pretty boring. It's just a little line segment. Here I have a hexagon. Here we have a badly drawn parallelogram. I mean, not just a random parallelogram, but a particular parallelogram, and so on. So this is the model of Mirkovic-Vilonen polytopes. And this is closely connected to the description which Bernstein-Zelevinsky used, which was based on something called Lustig data. I'll come back to that a little later. So these perfect bases, so here we have three general methods for producing perfect bases, and they all give the same combinatorics. Well, use some different models for the combinatorics, but I mean, the crystals, the graphs are isomorphic. That's the theorem of Bernstein-Zelevinsky I mentioned. So you might wonder, are these bases actually different as perfect bases? Like, are they actually, like, they give you some specific vectors in these representations? Are they different vectors? And the non-equality, but they are different. And the non-equality of the first two, that was resolved in the work of Kashiwara Saito. And the non-equality of the second two, or also the non-equality of the first and the third, so the fact that the MV basis differs from the other two, that was resolved in our work with Pierre. Oops, I lost the N in his name. With Pierre and Allen and Calder. So just recently, maybe independently, work of Fomin-Vilonen as well. But the first examples where they differ are not so small. They come in SO8, that's type D4, and SL6, type A5. So you actually have to go to like relatively complicated representations to find these vectors where the bases are different. So that leads to the following question, which is to find the simplest example of a representation with more than one perfect basis, multiple perfect bases. So it might be that the ones that we found are the smallest, but I don't know. I don't know any proof that that is the smallest ones, but maybe there's some other representations. I mean, I doubt there's other representations for which these bases differ for reasons that I'll explain later, but maybe there's some other exotic perfect bases around, and those differ from these ones in other examples. Not sure. So that's one open problem. And well, I feel this problem should be like amenable to kind of computer computation because the definition is relatively elementary of the perfect bases. And once I had a master's student to work on this problem unsuccessfully, but maybe somebody else will be more clever than we were and figure out how to program this, that you can actually compute this. Okay. So this is all about bases in a single representation. Now, as I mentioned, there's many representations, like they're indexed by some integer points in some lattice, like some z to the n. So it's maybe not convenient to have to worry about every single representation individually. So we'd like to study them all together. So there's a convenient way of grouping them all together inside a single algebra. Well, it was sort of closely related to there's maybe two sort of closely related ways. One, you can group them together in the functions on the basic affine space. I think Sergey mentioned that in his talk. Or for some reason, I'll do something slightly different here. Group them together into functions on n. So here n is the subgroup of G, which is like the upper triangular subgroup or maximal unipotent subgroup. So in the case of SLN, this n is just matrices with ones and diagonals and arbitrary stuff above the diagonal. And how does this embedding work? Well, basically you just take the highest weight vector to the function, which is just 1, and then you extend in the only possibility you can, which is invariant for the action of n, in terms of a formula. You can look at the formula, but maybe it's not super enlightening if you haven't seen it before. So here's an example also, which will hopefully make it more enlightening. So let's take G to be SL2. So in this case, it's very easy to say what all these irreducible representations are. They're just, you take polynomials in two variables, homogeneous of degree n. SL2 acts by kind of permuting the variables. And then, or another way of, more like invariant way of saying the same thing would be to say this is sim n of C2. Same thing. And you can embed this polynomials in two variables inside polynomials in one variable. In this example, the capital N of SL2 is just 2 by 2 matrices where you have an arbitrary thing in the upper triangular corner. So you might as well call it Y, and then you have polynomial ring in one variable as the coordinate ring. And that embedding just dehomogenizes the polynomials. So you have a polynomial in two variables, and you just get rid of one of the variables, set it to 1, and you get a polynomial in one variable. And so together that puts all these different homogeneous n polynomials in two variables inside a big polynomial ring in one variable. And so that's something similar like that we do for any group. Okay, so this Cn has, well, obviously it has a few different structures. For example, it's an algebra now, but also it has two actions of the Lie algebra n. It doesn't have any action of the group anymore, but now has two actions of the Lie algebra, which sort of come by differentiating the left and right multiplication of n on itself. So it's left and right actions of n. So I get two sets of these Chevalier operators, EI and EI star. And a basis of this coordinate ring of n is called biperfect if it's perfect for both actions. So with respect to left action and right action, if it satisfies the conditions I explained above. And so here's the theorem, I guess. I guess it appears in our paper. So with this we contributed to Fomin, Kamnitzer, Knudsen. If we have two biperfect bases, then they're isomorphic as bicrystals. So with respect to both crystal structures, so you have two families of crystal structures. And the second thing, which is that if it's SL2, SL3, SL4, then this coordinate ring has a unique biperfect basis. And again, this will fail for SL6 and SO8 because of those same reasons I explained above. And I don't know for sure what happens for SL5. Okay, so the fact that we have this now, rather than working with each representation individually, we work with this one big thing which contains all the representations. It gives us like a kind of master combinatorial object. So the master combinatorial object is called B infinity. So it's this bicrystal of Cn. And this is the combinatorial object, which we can use just to completely solve the tensor product multiplicity problem for any dominant weights. So if we have 3 dominant weights, then we just can count those crystal elements which satisfy these conditions. So they should satisfy a bound on epsilon I and a bound on epsilon I star, and they should have the right weight. And this idea basically goes back to Bernstein and Zelevinsky. That's how they solved the tensor product multiplicity problem. So obviously understanding really well this master combinatorial object B infinity is important. And fortunately, we kind of do understand it well. So first of all, there's this great picture which I think deserves to be better known. So I'll try it here. So this is a picture of B infinity for SL3. So once again, the blue arrows denote E1, the red arrows denote E2, the dots denote the basis vectors. So I have like the crystal elements. So here I have 1, here I have 1 in each. Here I have 1 and then 2, 1. Here I have 1, 2, 2, 1. And here I have 1, 2, 3, 2, 1. And well, you can imagine how it continues. And then the blue arrows, like they go up and to the left, sort of matching things, but counted from the left, whereas the red goes up and to the right, matching things counted from the right. And then there's also the second family, the star crystal operators, which I didn't draw because it would make that clutter the diagram, but let me just draw like, I don't know, one of them just so you get the idea. So the star crystal operators do the same thing, except now counted from the opposite side. So that's a E2 star guy. Whoa, it's really hard to read that. Better convert back to the. Anyway, this guy here is an E2 star. So the same, so sometimes they'll coincide with the original ones, but when things are getting tight, when there's like a sort of a decrease in the amount of lanes and you have to squeeze over, the red squeezes over from the right and the red dotted red, the EI star squeezes over from the left. So this is a picture which really enables you to visualize exactly what this B infinity looks like for SL3. Of course, in general, you might not want to visualize it. You might need some kind of concrete combinatorial model. So again, this can be provided using the theory of MV polytopes. It's quite convenient, or equivalent theory of Lustig data. So I don't want to get too much of the combinatorics because it takes me too much afield. But I do want to say one important thing about it. One way to think about either this MV polytopes or Lustig data is you can think that B infinity is naturally in bijection with the tropical points of the flag variety, but maybe for the Langlands dual group. So this is, maybe I'll just write that out because it's a little mouthful. So this is the tropical points of the except also satisfying this greater than or equal to condition, this satisfying some non-negativity condition. and this description of B infinity, well, basically goes back to Bernstein-Zelevinsky. They didn't phrase it in terms of exactly crystal language, but basically goes back to them, and then maybe some modifications of this, elaborations on this are in my work, and then also in Goncharov Shen. Okay. Great. That somehow like ends the first part of the talk, and it's been exactly half hour, so it's a good timing. Maybe it's a good place to pause for a second and see if there's any questions. I see a hand up. I don't hear anything. I don't know if there's some.
Has the existence of biperfect bases been proved?
Oh, yeah, I should have said probably that those guys that I mentioned above, dual canonical and so on, semicanonical and V base. Well, here I was talking about perfect bases for each V lambda. They all gather together to form biperfect bases for functions on N. So these all give you, like maybe I should have said this more. Let's say it.
Thank you. Any other questions?
Let me just say one thing just to make sure that this part about the biperfect bases was clear.
One more question.
So, yeah, let me just finish answering the first one. So like, somehow there's a equivalence between sort of like compatible collections of perfect bases for each V lambda and a single biperfect basis for Cn. So you can go back and forth between having a biperfect basis, it gives you a, restricts to a perfect basis for each V lambda. On the other hand, if you have perfect basis for each V lambda, you get a biperfect basis for Cn. So hopefully that makes it more clear. So all those examples, they were compatible collections. They'll glue together to give a biperfect basis for Cn. And now I'm ready for the second question.
Is it possible to have non-isomorphic modules, both with a basis in the sense that you're talking about, where the bases are the same? So does the basis determine the isomorphism type of the module?
Well, I mean, a basis is like a vectors in some vector space. So if the representations are different representations, they can't have the same basis. Maybe I'll interpret your question then slightly differently. Is it possible for the two crystals, this underlying combinatorial structure of the graph, to be the same if the representations are different? And
that's what I meant.
Yeah, right. Thanks. That's a very good question. And the answer is no. So that completely determines the representation. So if you see a picture like this one over here, you instantly know what representation it came from. I mean, in some sense, for a sort of stupid reason, because this encodes the weight diagram, right? I mean, from here, you can get the weight diagram just by remembering how many dots there were in each spot, like remembering this weight function. And that alone determines the isomorphism type of the representation. That's like a, I don't know, basic fact about representation theory of semi-simple groups.
Okay,
So,
we might have some questions on Zoom.
Yeah, I saw. It says, what do we know in general for the distribution of the weight multiplicities tensor product structure coefficients? I'm not sure what you mean by distribution. Do you want to ask your question out loud or Paogui? Unimodality. Oh, those kind of questions. Well, I think there is a lot known about that, but let's say that's not the topic of, of this talk. Actually, in terms of tensor product, this kind of numerical kind of thing about tensor product multiplicity is probably the most famous thing people study is the saturation conjecture, but well, which was solved for SLN by Kamnitzer and Tau, and in general, other people have worked on it. But anyway, it's not the topic of today's talk. Yeah, so somehow I like cheated because I started telling you that I wanted to find these numbers, and now I'm not really going to talk about those numbers at all, even though it's a Combinatorics conference. I'm actually talking about basics, even though I did a little bait and switch on you.
Okay,
Any
let's
other
just keep going.
Okay. Great. Okay, so now comes to the second half of the talk. And now maybe like the first part was maybe more standard. Now things are going to become more speculative. Okay, so let me say what now. One thing is speculative. So now we're going to start talking about cluster algebras. So first of all, I should say that I'm not at all an expert on cluster algebras, and there's like lots of experts on cluster algebras in the room, probably also other ones on Zoom. So I apologize for any mistakes I made. Fortunately, it won't be able to like track me down and complain if I do say something wrong. Okay, so a cluster algebra, and I think the cluster, I'm going to be talking about what's called upper cluster algebras, in case you aren't an expert. So it's a commutative algebra, along with a collection of certain subsets of the commutative algebra, finite subsets, called seeds. So I have a big algebra, and then many of these collections, infinite, possibly finite or infinite, subsets of the cluster algebra. And each of these subsets has the property that the algebra contains the polynomial ring in that subset and is contained inside the Laurent polynomial ring in the subset. So the algebra is almost the polynomial ring, or you could say it's kind of on the same size. It's the polynomial ring, but a bit bigger and not quite as big as the Laurent polynomial ring in the cluster. I'm sure many people have different ways of introducing cluster algebras. This is the way I think about them. And maybe what's more important though, or it's also important, is that if you have one of these seeds, so some n of these elements in your cluster algebra, there's a process called mutation, which allows you to take one of them out and get a new one. So you pass from these x1, xn to a new collection, x1 prime, x2 up to xn. And you can do this as long as the variable isn't what's called a frozen variable, in which case it can't be mutated. And somehow the process for doing this mutation is related to what Sergey talked about with those graphs earlier. Okay, so now I explained it. So these cluster algebras were introduced by Fomin and Zelevinsky. And one of the main motivations was to study these canonical bases. So here was a theorem of Bernstein, Fomin, and Zelevinsky, which is that the coordinate ring of this N, upper triangular matrices or unipotent, maximal unipotent subgroup, has a cluster algebra structure. And the only thing I'm going to tell you about it is that every reduced word for W naught, so this W naught, this means the long element of the Weil group, so for example, for SLN, this would be the longest element of the symmetric group, the element which completely switches things. Every reduced word for W naught gives a cluster. And these are only some of the clusters. There's some clusters which maybe don't come from such reduced words. Okay, there are maybe some clusters that don't come from reduced words, but every reduced word gives you a cluster. In the theory of cluster algebras, the cluster algebra is kind of completely determined by this initial cluster and this transformation matrix or this quiver. So you can, using just one reduced word, it actually determines the whole cluster algebra. So why is this cluster algebra kind of structure interesting for our purposes? So when you have a cluster algebra, what can you do? Well, you have these different cluster variables. So you start with some initial cluster, maybe it has x1, x2, x3, x4. You mutate, and so you gain a new cluster like the one that's shown in the green here, which has x1 prime and not x1. And then you do another mutation, and maybe you get now an x2 prime. You get rid of x2 and bring in a new x2 prime. So this gives you a whole lot of different, what's called cluster variables. And once you have all these different cluster variables, you can start forming cluster monomials, which means you look at one group cluster and you take monomials of the things in there. So there's another example that came from the orange group over here. So produces you many different things called cluster monomials. So there are monomials in a single cluster, but working over with all the clusters. And in a cluster algebra, the cluster monomials are always linearly independent. Well, I think it's like probably some famous conjecture, but I think in different classes of cluster algebras, it was proved at different times. And one proof is related. I think the state of the art is the work of Gross-Hacking, Kilk, and Savage. But again, I'm not an expert, and I wouldn't dare to try to summarize the work on this kind of thing. But let me just state it as just a fact. Okay, so let me just show you an example of how this works. So relevant example for us. So let's take SL3. So we end up with 3 by 3 matrices with ones and diagonals. So we have 3 coordinates, x, y, and z. So of course, this ring is just a polynomial ring of 3 variables. But that turns out to be not the right basis to take. For example, it's not a biperfect basis if you just take the polynomial ring in 3 variables. I mean, not the polynomial. It is a polynomial ring in 3 variables, I should say, but the basis you want is not just the obvious basis of the polynomial ring in 3 variables. So how do you make from the cluster algebra point of view, we have 2 clusters, turns out. One is the x, z, and this x, y minus z, which can think of as like a little 2 by 2 determinant here. And the other is y, z, and the same 2 by 2 determinant. So these 2 guys, they live in both clusters. They're what's called frozens. And then the mutation just swaps these 2 guys back and forth. So from a cluster algebra perspective, it's a very simple cluster algebra. And then the cluster monomials, well, you just take together all the monomials in the first group and all together the monomials in the second group. And it's not like that obvious, but if you stare at it a little bit, you'll see that this is a basis of the polynomial ring in 3 variables. Not the usual basis, but a basis. And from the perspective that I was advertising in the first half of the talk, this is a very good basis. It's biperfect. And in fact, it's the unique biperfect basis. So it's not hard to prove that in this SL3, this Cn only has 1 biperfect basis, and this is it. Okay. So I'm trying to emphasize, like, we have 2 different worlds. One is this representation theory world about wanting to study tensor product multiplicities and perfect basis and so on. And the second is this cluster algebra world. And look, both worlds give us the same basis. Now it's not really like a huge surprise because Zelevinsky was Fomin and Zelevinsky were in both worlds or something when they invented cluster algebra. So it's not a total accident, but it is a little bit striking that we see the same basis coming from 2 sides. Okay, so that brings up the obvious question, like, how are those bases that I talked about in the first half of the talk, how are they related to cluster algebras? So we have the following theorem. So that the dual canonical and dual semi-canonical bases contain all the cluster monomials. So all those cluster monomials, they live in both these bases. So I think for the dual semi-canonical basis, this is definitely due to Geist-Kirk-Shor. This is from about 10 years ago. For the dual canonical basis, as far as I know, it's due to Kang, Kashiwara, Kim, and O, and maybe independently to Fan Chin, but just from a few years ago. So it's slightly hard for me to believe no one ever established it before. So maybe somebody knows the earlier work in this direction. I don't know. And of course, obviously now we have let me call this the first real serious open problem that I want to pose. Does the MV basis, so that was the 3rd family of perfect bases, does it contain all the cluster monomials? So somehow these works are not so easy to prove that it contains the cluster monomials. So basically they come about because this dual semi-canonical basis is related to what's called additive categorification of cluster algebras. And the dual canonical basis is related to multiplicative categorification of cluster algebras. So it would seem that in order to solve this problem, you would need to see some kind of categorification of cluster algebras being related to the MV basis. And well, I thought about it and other people have thought about it. We don't have any really good ideas for how to do it. So somehow you have to understand this cluster mutation rule in terms of this, the geometry that's underlying the MV basis. Okay, so there is okay, I said there's not much, there is some actual solid work in this toward this problem. I should have said that right away. So due to Bowman, Gosson, and Littleman, so just from last year, they proved that for reduced words for W naught satisfying a certain condition, and this condition is kind of technical, and I think that there's no known words which don't satisfy that condition. So it might be this is just true for all the words, that all the cluster monomials in those clusters lie in the MV basis. So remember I said that some of the clusters come from reduced words for W naught. So for the cluster monomials from those clusters, this result will show you that the MV basis does contain those cluster monomials. But then there's lots of cluster monomials which, there are lots of clusters which don't come from reduced words, and so lots of cluster monomials from these other clusters. So, well, their work doesn't solve this problem. Okay, so there's an important distinction in cluster algebras called a finite type. So which means that there's only finitely many clusters. I think in terms of Sergei's pictures from earlier, that means that there's only finitely many, actually, I shouldn't say anything because I might say something like that. Okay, when the cluster algebra is finite type, then it's known that these cluster monomials form a basis of the cluster algebra. So in general, though, the monomials, these cluster monomials are not the entire, will not give a basis, but when the cluster algebra is finite type, they do give a basis. But this cluster algebra Cn is finite type only in some very small cases. I think SL2, SL3, SL4, SL5, and also SO5. So there's like an easy confusion which you can make, which is there's a Dynkin diagram sort of associated to every finite type cluster algebra, and it's a different Dynkin diagram. So like, yeah, for example, well, I won't even, anyway, these guys are going to be associated to some other Dynkin diagrams, which are their cluster type, their finite cluster type. Okay, but these are the only semi-simple groups for which this coordinate ring of n is of finite type. So in these cases, we have a basis of cluster monomials. Okay. So here's another non-open problem from the theory of cluster algebras, which says, if we have a cluster algebra which is not finite type, can we extend the cluster monomials to a basis? So we have all those cluster monomials around. They don't form a basis, but they are linear independent. So we'd like to extend them to a basis. Of course, you know, in your first course in linear algebra, you learn that, you know, any linear independent set can be extended to a basis. But maybe, so this problem is obviously can be solved, but maybe can you give some construction of that basis? So this basis should satisfy a certain property. So I learned of this definition from Fan Chin. Maybe it's known beforehand, like going back to the work of Fomin and Zelevinsky. Cluster algebras 4, maybe. Anyway, I'll use this Chin's notation. So he says a cluster algebra with a cluster is called, so what is it? A is the name of the cluster algebra, not a cluster algebra. So A is the cluster algebra. X1, Xn is a cluster in it. And then I have some element in the cluster algebra, and I say that element is pointed at some element of z to the n, which is called the g vector. If this element is like x to the g, so some Laurent monomial in the x's. So it's not necessarily a cluster monomial, because it's not a monomial, but it's a Laurent monomial in x's, plus some lower order terms. So these are lower order with respect to a certain partial order on the Laurent monomials. And this partial order somehow depends on what cluster you're in. And a basis for your cluster algebra is called good, so not to be confused with the good bases that I was talking about earlier. For the representations, if it consists of elements which are pointed with respect to every cluster. So you want something and it should be pointed in every single cluster. And so these good bases they can be encoded combinatorially by this data of this G vector, right? Because so A is going to be like completely determined by this G, because in any other, well, I guess not totally obvious, but anyway, it's also true that A will be completely determined by this first exponent. So these good basis vectors are parameterized by these G vectors. And if you change which cluster you're in, this G vector transforms according to a certain mutation rule, which was introduced by Fomin and Zelevinsky, maybe also independently by Fock-Goncharov. In this way, a good basis will be parameterized by like Zn once you fix a single cluster. So, but if you take as a disjoint union over all clusters, then you'll get a different G vector for any cluster, and then there's some compatibility of those G vectors, which is this this G vector mutation rule of Fomin and Zelevinsky. So that these good bases, where if you have a good basis, it's parameterized by the G vectors up to this mutation rule. And this idea was interpreted by Fock and Goncharov as saying that it's in bijection with the tropical points of the dual cluster variety. And this is sometimes called the Fock-Goncharov conjecture, the fact that there's a good basis parameterized by tropical points of the dual cluster variety. So a theorem of Chin is that every good basis contains all the cluster monomials. So I think that there's three general families of constructions of good bases for cluster algebras. So what I want to do now, in the last speculative part, is I'm going to show you how these families of good bases match up with these families of bases of biperfect bases for Cn in the special case when the cluster algebra is Cn. So first of all, we have these generic bases, which were, this is like a super long history. There's no way, I don't know the history too well. Lots of people were responsible for this development, but maybe Calderon and Chapoton was the initial motivational work. And in that way, they come from what's called cluster characters in these additive categorifications of cluster algebras. And then Geis, Leclerc, and Schur proved that in fact, in the case of Cn, this generic basis coincides with the dual canonical basis. And then there's a basis, which at least Chin calls the common triangular basis, and also probably has a long history, and also probably other people call it other things, but it corresponds with the dual canonical basis. And again, it comes from monoidal categorifications of cluster algebras. Simple objects in monoidal categorifications of cluster algebras. Let me write that down. And finally, going back to where I started the talk, when I was sitting in the park 5 years ago and David Spire said to me, "Oh, have you heard of these theta bases?" Or more precisely, what do representation theorists think of this thing? Well, I didn't know anything about it then, but now I still don't know much about it, but there is such a thing called the theta basis, which was introduced in a celebrated work 5 years ago by Gross, Hacking, and Kiel and Kinsevich. And the problem I want to pose is today, is sort of the main open problem, is whether this coincides with the MV basis. And I'm going to show you a tiny piece of evidence in favor of that. So the tiny piece of evidence is the following. If we work with our favorite two counterexamples, SL6 and SO8, so then we have three bases that differ: the MV basis, the dual semicanonical, and the dual canonical. They're all different. Let me call the corresponding guys who are different B, C, and D, okay? And then there's some vector V, which is going to be some vector which actually lives in all three bases. It's some actually a frozen guy who's just around and helping to account for the difference. Then we have the following pattern. This dual canonical basis vector is the MV basis vector plus this auxiliary vector, and almost the same thing is true here. Here we have C is B plus 2V. Okay, so the smallest one in some sense is B, and then if you add one of these V's to it, you get D, and if you add two of these V's to it, you get C. fine. I mean, it's a computation you can do, not very easily, but you can do it. In when you do it, like because of this definition of the MV basis vector, this kind of computation ends up being about the study of certain varieties and how they degenerate, and it's like well, involved computation, but you can do it and you get this. And the exact same pattern is seen if you look in what's called rank 2 affine type cluster algebras. So I think for this particular cluster algebra, it's impossible, as far as I know, to figure out to do the matching computation. Like it's not possible to determine the theta basis because it's too complicated, as far as I know, for this cluster algebra and do the same computation. But there's like an analogous kind of computation you can do, which involves this rank 2 affine type cluster algebras. And in that analogous computation, you see exactly the same pattern. So this kind of, I guess, Leclerc pointed this out to us. I mean, it's not really his computation, but well, I guess he did have a paper about this. So, and he has a paper about this, and he pointed out to us the similarity. So the fact this similarity is what motivates this idea that, well, I could say a conjecture or a problem that the theta basis and MV basis coincide. I'll stop there. Thank you.
Okay, thank you, Joel. Any questions? Yeah, okay. Let's do it.
Hi, Joel. So I don't think you explicitly answered this. Does every perfect basis contain the cluster monomials? Do you know?
No, I don't know. I didn't. Yeah, I didn't even state that as a problem. But you could ask that as another open problem. I actually suspect the answer is no. The reason why I suspect the answer is no, because the definition of perfect basis or biperfect basis is not a very like seemingly rigid kind of thing. It's a little bit ad hoc. So I sort of think the answer is no, but I'm actually not sure. So it can be another open problem. It's a good problem.
Okay, I'm going to the next question, but I will ask question in the meanwhile. So there are some bases which come from skein series. Do you know if they correspond to any of the three you mentioned?
Let me just write down the question. Does every biperfect basis contain the cluster? Yes, bases from skein theory. So yeah, that's a good question. There's a couple ways of interpreting your question, which is because there's these bases from skein theory are usually not bases of the representations themselves, but bases of like directly bases of these kind of tensor product multiplicity spaces or invariant spaces in tensor products. Generally, those bases and really, these bases only really work very well in SL3. I mean, you can make bases in other SLNs. I mean, I worked on it. But even in SL3, those bases, I think, are different than the bases I'm talking about. So I think so at least it was definitely shown that the bases don't coincide with the canonical basis by Kovanov and Kuperberg, I think, for SL3. But I think that generally these kind of web bases from skeins would not coincide with any of these bases. I mean, I like the web bases, but they just won't have any of the really good properties that these kind of bases have.
Okay, thank you.
Looking at the basis elements that you wrote down in that special case, just if you scroll up a little bit, I mean, there's that looks like the MV basis element in this case is sort of preferable with respect to some kind of positivity, that it's sort of like less positive, and then the other ones have some extra stuff that's been, or I don't know if that's, sorry, that's kind of based on some intuition that's maybe vague intuition coming from cluster algebras, where there is some kind of notion of positivity that makes you think that, you want to say that B is like the smallest thing that gives you things to be positive, and then you added in these V's and maybe you shouldn't have. And does anything like that make sense in the representation theory side?
No, I mean, not, it's a good question. And as you say, from the cluster algebra point of view, like the manifestation of that is, I guess, that this theta basis coincides with the greedy basis.
Right.
For rank 2 cluster algebras. But besides that, I don't know anything. Like, I don't know any, from the representation theory viewpoint, I don't know any sense in which the MV basis would be minimal or some way of characterizing it. No, I have no idea, but it's a good question.
Okay, do we have any questions on Zoom maybe?
Yeah, there is one question. It says, does the MV basis have non-negative integer structure constants like the theta basis? That's a good question. And the answer is yes. So yeah, one maybe evidence for this, my conjecture or problem here, is that, yeah, so the MV basis and the theta basis, so they're both bases for the coordinate ring on N. And you could ask, when you multiply two of these basis vectors, what can you say about the coefficients? And for both bases, the resulting coefficients are non-negative integers.
So MV and canonical basis have this positivity property, but semicanonical basis does not. Is that right?
No, I think MV and the theta basis have this property. For both these two bases have this.
Doesn't canonical basis also have positivity property?
Maybe it's true too. I'm just trying to think if it's the same positivity.
Okay, there's another question, I think, on Zoom.
Yeah, maybe it's also true about this canonical basis too.
There was a question from Greg Miller, maybe.
Okay, let me read it.
I was just, someone had asked about the connection to skein algebras, and I was mentioning in the SL2 case, Chin mentions the connection to the bands, bangles, and bracelet spaces in his note. Wasn't a question, I was just an aside.
Thanks. Yeah,
Okay.
yeah. For SL2, it's somehow less surprising that things will coincide. The skein algebras are very well behaved, I guess. So there should be some easy connections there. Well, I know easy, but like they should work. I mean, these things are more complicated. What Greg's referencing is some thing like a little orthogonal to what I was talking about, where you work with surfaces. So you can sort of I somehow you can do everything much of what I said, but where you also input a surface, but I didn't talk about that today, and don't know as much about that.
Okay, so I think we have a lunch break. Let's thank Joel again. And shall we try to have some kind of discussion with Joel, maybe on Zoom? Okay, so how about especially young people, but everybody else too, if you want to, I think we could come forward and you can have a discussion with Joel on Zoom or using this microphone, I guess. Yeah.
Joel, can I ask a question?
Yeah, go ahead. You're not a young person though.
I know, that's why I was trying to wait. I can give a little bit more time.
I'm just joking. They're probably still coming down to the front or whatever. Go ahead.
Do you know any intrinsic characterizations of any of these three bases on the representation side, like a property that this basis is the one with this property, and if you have this property, you must be this basis?
I guess for the quantum group, for the canonical basis, if you go to the quantum group, then we have the property that it's invariant under the bar involution. And that together with the upper triangularity will uniquely, like upper triangular with respect to PW basis, that will uniquely determine it. So it's true for the canonical basis, but not for the other two. That's somehow what I meant at the beginning when I said that the canonical basis is like a more rigid kind of thing, that it actually is kind of canonical. You can define it in